Hello, my name is Eric. This is a second video in a two-part, and probably actually a three-part series on techniques for integration, which of course is a calculus topic. And loosely it's organized around the theme of finding antiderivatives, but also some graphical and numeric methods for when maybe you can't find an antiderivative, such as this problem here, which is we did problems 1 through 3 in the previous video. Feel free to watch that. This is the fourth problem in this review, and it involves creation of what's called a slope field. So how does that go? Well, here's the idea. You go to a grid point and you think about what is the x and the y there? Oh, okay, clearly it's 2 and 0. Well, the formula for the derivative says 1/2 times x times y. So at that point, the y prime value is 1/2 times 2 times 0, and that computes to be 0. Now, what does it mean to have a zero derivative? It means y values are not increasing, y values are not decreasing. It means you have a horizontal tangent line. What we do is draw a tiny little segment of that tangent line, and we just repeat the process somewhere else, of course. Let's go up to this point, which is 2, 1. And if you were to plug those numbers into the calculation for that derivative, you would get 1/2 times 2 times 1, which is 1 times 1, which is just 1. So that tells you have an increasing graph at a rate of 1. What does the slope of 1 look like? Well, it's 1 over 1 up. So it's aiming for this point up here. So you draw it at about 45 degrees like that. And repeat the process. How about this point? That's 1, 1. Okay? So if I have 1, 1 for x and for y, what's y prime going to be? It's going to be 1/2 times 1 times 1. Which makes a half, which is not as steep as this. A slope of a half should aim for 2 to the right and 1 up. So I'm aiming for the same point out here as this one was, but it's just less steep of an angle. And so you draw a tangent line, but just a little segment of a tangent line for this so-called slope field. Now, are there any points up here that are really easy to compute? Yeah. All the points on the x-axis are easy because of the same thing that happened here. Here's the point 1, 0. Okay, we'll do one more of these. The derivative here is going to be 2 times 1 times, or excuse me, 1/2 times 1 times 0, and that's going to make 0 again. That's going to happen here. That will happen here, here, because at all these points, the value of y is 0, and that's going to kill the derivative and make it 0. It's also going to happen here, though, because along the y-axis, you get x's that are equal to 0. All right, so the rest of these points, are there shortcuts for those? Yeah. But let's go ahead and finish the first quadrant, and then we'll talk about how we could possibly use this information over there to save us some time. Here's another point. It's 2, 2. The derivative is 1/2 times x times y. That's half of 4, and that's 2. And so this is going to be the steepest thing we've seen so far. It's either going to aim at a point way up here, or it's going to aim down at a point over here. And so I would draw it about like this. It needs to be pretty steep. Here's the point 1, 2. The y prime there should be 1/2 times 1 times 2. That just makes 1. So at this point right here, you get a slope of 1, which aims like this. Okay, first quadrant's complete. The x-axis is complete. The y-axis is complete. I only have 4 more of these I have to do. And I think I'm going to do just one of them. This one. This is the point -1 positive 1. Negative 1, positive. It's got a derivative of 1/2 times negative 1 times 1. But that makes negative 1/2. And if you think about it, over here we got positive 1/2. Over here you're dealing with the same numbers, you just have you have a negative sign that you didn't have here. It's still 1 and 1. So this slope ends up looking like that slope, except this is 1/2 and this is negative 1/2. Negative 1/2 aims for that. Down 1, right 2. So not so steep there. And you can make the same argument about the rest of these 3 points if you're looking for a way to save time. Okay, let's do this one. Yeah, same numbers as here, but this has a negative sign when this didn't. So if this slope was positive 1, I think it was, this slope should be negative 1. And aim for that. If this slope was positive 2, this slope should be negative 2 and aim for that. So we're just looking for ways to make this go a little faster. If this slope was positive 1, this will be negative 1 and aim for that. And you have just drawn yourself a sloped field. What's the idea behind it? Well, they're not asking us. But if they were, they might next say, hey, we have a point on the curve that when x is 1/2, y is 1/2. Where's the curve? And then they want you to trace through here something like this. Okay, just sort of going with the flow, not against the grain. Working with this same derivative, we're supposed to solve a differential equation by separating it subject to the condition f of 0 equals 1. And then I think we're going to be done with that. So let me write that up here. And also the condition. And I'll slide this up and give myself some space to work. All right. We did a video on separable differential equations. If you're not familiar with these, the idea is using only multiplication and division. You want to rewrite this equation so that probably all the x's and dx's are on the right, all the y's and dy's are on the left, or vice versa. Doesn't really matter where they are, they just need to be together. And you don't want to be dividing by dx. So first things first, let's multiply by dx and cancel. Then we don't really want this y over here. He needs to be over with his y differential. That's accomplished by dividing by y. Okay, it's separated. The second step is to integrate. Find antiderivatives. Antiderivative of y is the natural log of the absolute value of y. Excuse me, of 1 over y, okay? Antiderivative for this, you just take the exponent 1 and raise the power up to 2, and then don't forget to divide. So it's 1/2 divided by 2 is 1/4 x squared. Put a constant on here somewhere, a, b, or c, your choice. And we're about 2 steps from the finish line. Let's go ahead and get this y out of this log by a step I like to call exponentiate, meaning use these as exponents sitting on top of an e. That looks like this. Why? Well, because it's going to take advantage of the inverse nature of exponents and logs. You're going to be down to just absolute value of y. Now, over here, I'm going to rewrite this power as 2 powers multiplied together. And I'm going to designate a letter C to represent e to the b. This step is more cosmetic than anything. You don't really need it, but we do it. It's traditional. So now I have absolute value of y equals c times e to the 1/4 x squared. And the last thing to do is to take off the absolute values. I like to call that exfoliation. Exfoliate, peel away those unwanted absolute values. And you're left with y equals c times e to the 1/4 x squared. Plus or minus. Okay, remember, don't get caught letting a negative thing equal to something that has to be positive. You can fix that by accounting for both with a plus or a minus. All right, let's start the next problem. A function g has the derivative given by the formula dy dx equals 2x plus y. It is known that values of g are positive when x is between 1 and 2. So all they're saying is if you're studying this function between x equals 1 and 2, you can be certain that the y's are positive values also. This whole thing takes place somewhere in the first quadrant, okay? Now, given the initial condition, g of 1 equals 4, and a step of 0.5, use the Euler equations. Oh, the Euler equations to approximate g of 1.5. By the way, how far is it from 1 to 1.5? It is 0.5. So this is a one-step Euler solution, which basically means it's just a sort of a tangent line approximation. But let's just go ahead and do it like an Euler. Write down a table. You can see this in one of my other videos. The formula for a new x value is to take this old x here and make a new one by adding a step. You just add a step. So the equations Euler gave us are a new x is an old x, either increased or decreased by some kind of a step, delta x. So what's 1 plus 0.5? 1.5. Now that's a new x, okay? The reason I keep it in this column where it says old x is because sometimes this Euler thing goes recursively for many, many steps. The harder one to compute is the new y. And that's given by the old y plus y prime times dx, or I guess delta x. But this is, in fact, a differential for y over here. And so that's what we're going to do here, is go take the old y, add y prime times delta x. What is the old y? 4. Okay, hold on tight. What is y prime? It's that formula up there, but you're supposed to substitute into it the x and the y from here. So 2 times x becomes 2 times 1, plus y becomes plus 4, times the step, which we told you was 0.5. Let's see if we can do this in our heads. 4 plus 2 is 6, half 6, 3 plus 4 is 7. Bring that down, and that's the so-called Euler approximation of g of 1.5. And you should write a little report. Say g of 1.5 is approximately equal to, but not necessarily the same thing as 7. Okay? That's part A. Let's see what else is in store. I'm going to need some of this information, so let me write it down over here in the margin. Part B. Show that the formula for the second derivative is y double prime equals 2 plus 2x plus y. Well, a second derivative is just the result of doing a derivative to the first derivative. Y double prime is nothing more than the derivative applied to y prime. And that is this formula. Okay, what's the derivative of 2x? 2. What's the derivative of y? Y prime. Now how come it doesn't come out looking like they advertised? Well, the answer is you need to go substitute this back in for y prime. So take the y prime out, put the 2x plus y in, and you made it look like they wanted you to. Part C, compute the value of y double prime at the point 1, 4. Y double prime evaluated at 1, 4 is 2 plus 2 times 1 plus 4. I think that makes 8. Is that right? Yeah. Okay, in part A of this problem, you computed an Euler approximation. Remember we got g of 1.5 approximately equal to 7. Explain why your Euler approximation underestimates g of 1.5. Okay, here's what Euler said. It's going to be somewhere around 7. How do you know that's too low? The answer is I'll explain this with a graph, but you need to know how to explain it in words. The formula for the second derivative was 2 plus 2x plus y. Okay, that's important. So here's what you should say. There's a point on the graph of g. Okay, it's not going to hurt to put an illustration or a graph in here like this, like I'm doing, but you have to be able to write this out in your words. Use your words. You got to use words. The way you know this is underestimation is because this graph is increasing in concave up. Now the increasing part's not important. The concave up part is. So all you really need mentioned is that you know you have a graph that's concave up, but you have to be able to defend that. And since the graph is concave up, and since a one-step Euler solution is just really, you know, a linear approximation, basically a tangent line calculation, this g of 1.5 equals 7 thing is somewhere up here on this tangent line. It's lower than the curve. So you'll have to go through and write something like this. You remember the assumptions of the problem. They said that for x between 1 and 2, y is positive. It is known that the y values are positive. And that's by assumption. Since y double prime is given by this formula, and x is greater than 0 and y is greater than 0 in this interval, or more importantly, I guess, in this interval, this calculation for y double prime is positive on the same interval. And the graph, now be specific and say which graph. The graph of what? The graph of g concave up. The graph of g is concave up. The linear approximation that we did previously, g of 1.5 approximately equal to 7, underestimates the actual g of 7 because the tangent line is lower than the curve. below the graph of G. Okay? Now they're going to ask us to do one more Euler solution. I'll give you a half second to finish reading that, or pause the video if you need to. I'm going to move on to this part E here. Part E says, given the initial condition G of 1 equals 4 in a step of 0.5, use the Euler equation as an approximation. Get an approximation for G of 2.5. So this would be, and we've already actually done the first step of this, I think. The step size is the same, the starting place is the same. The Euler equations are the same. Okay, so I think what we're going to have is, if you look back to the one we did, we had x old, we have y old, and then we had a calculation for the new y, which was y old plus y prime times delta x. And let's see, the derivative was 2x plus y. So that would go here. And when we set this up previously, we went ahead and took the initial condition 1, 4, put it in there, got a new y by taking the old y and going 2 times 1 plus 4 times the step. The only difference is last time we were basically done. We made a new x by adding 0.5. Remember that? Okay, just add 1 plus a step, 0.5. This turned out to be half of 6 is 3 plus 4 is 7. Okay, well, we have to go farther this time. They want us to move on from 1.5 to 2 and from 2 to 2.5. And hopefully the math won't be too hard. How do you get a new y to bring down here? The answer is you take this old y. It's 2 times the old x plus y, which is 7, times 0.5. 2 times 1.5 is 3 plus 7 is 10. Half of 10, excuse me, is 5 plus 7 is, I'm getting 12 out of this. So this one was 7. This one's 12. Let's do it again. Take the old y, 12, 2 times the old x, plus the old y, because that's the formula for the derivative, times 0.5. And these numbers are getting rather large. 4 and 12 is 16, and half of 16 is 8 plus 12 is 20. There's one more problem. I think I'll stick it in the next video. It's if you don't need to know anything about logistic growth, you can skip the next video. But the last segment of this review explores something called logistic growth and the logistic equation. Thanks for tuning in. I'm Eric, and have a great day.